Swayam Prabha. Digital India. Educated India.
In the previous lecture, we analyzed a problem in moving contact lines involving a thin film. And we found that the problem exhibits shear stress singularity at the contact line, which results in a logarithmic divergence of the tangential force as well as quantities like dissipation, which also diverge. I had mentioned that the singularity is not a feature of the restrictive lubrication approximation problem, but is rather a generic feature of contact line models in general. Now, this discovery was made in 1971 by Hearn Scriven when they analyzed the flow in a wedge. Their work itself was an extension of the work by Professor Keith Moffat, who analyzed motion in a wedge, and Hearn Scriven extended the Moffat solutions to the problem of a wedge where you have a wall on one side and then you have an interface. So a typical geometry that Hearn Scriven studied is a simple geometry of Hearn Scriven's problem is shown on the screen. So you have a solid wall which is making an angle alpha with a flat interface. Now they assume the interface to be flat because the argument was that even though in reality the interfaces are curved, if you go sufficiently close to the contact line, the interface will practically appear flat. And further, curvature in the lateral direction also disappears. Therefore, you can analyze it as a two-dimensional problem. At least it's expected that the leading order solution is a two-dimensional problem. That was the argument. So this problem, the solution of this problem is really, in some sense, only a local solution. It's a local flow very close to the contact line. We will also see that the solution is local in a very peculiar sense. The solution will not be valid very, very close to the contact line. It will also not be valid far away from the contact line because of the assumptions that were made, such as the interface being flat and absence of inertia and so on. So in some sense, this solution that Hearn Scriven found should ideally be thought of as a solution that is juxtaposed between a microscopic solution for which a lot of research is currently happening, as well as a macroscopic solution which would vary from problem to problem. So let me first discuss the general setup of Hearn Scriven solution, and then we will look at their solution for a very special case so that the analysis become easy and tractable, and we won't spend too much time on messy calculations, but rather look at the main essence of the paradox. So the analysis of Hearn Scriven, essentially it was a two-phase flow, and they had two liquids which is separated by a flat interface. The argument is that if you go very close to the interface, very close to the contact line, near the contact line, inertial terms become small, okay, because you can define a local Reynolds number. A local Reynolds number which would be defined as velocity into r by nu, where velocity is the velocity of the plate, becomes very, very small as r goes to 0. That was the argument. Okay. Now, once you say that the inertial terms drop out, then the equations are governed by the Stokes equations, and the Stokes equations essentially become minus gradient of P plus mu del square of u becomes 0, Now again, you are so close to the contact line. We are very close to the contact line. Contact line. Gravity becomes small. Small at that length scale. So I'll connect this to a macroscopic flow and say what exactly is Hertz's given solution. So if you say that this is my Stokes equations, and if you say that the fluids are incompressible, then you can eliminate pressure by stating that we can take the curl of this equation essentially gives me curl of a gradient of pressure plus mu del square of curl of u becomes 0, and I get del square of omega becomes 0, where omega, which is nothing but the curl of u, is the vorticity. Okay. Now since we are in 2 dimensions, omega is nothing but omega of you can say Ez, where Ez is perpendicular to the screen, to our view. Okay, so it's practically a scalar. So you can say treating omega as a scalar, because there's only one component of omega that is non-zero, then we simply have del square of omega equal to 0, right? That's what we have. Now you can also say del dot u is 0, right? So in 2D this essentially becomes del u by del x plus del v by del y is 0, and define a stream. This allows us to define a stream function which is u becomes del psi by del y and v becomes minus del psi by del x, and we simply get now we simply get del omega to be del v by del x minus del u by del y. That's the z component of vorticity, and this simply becomes minus del square psi by del x square minus del square psi by del y square, and this simply becomes del square of omega, del square of psi. Now if I substitute this omega is minus del square of psi into the equation, I get del power 4 of psi is 0. Right? This equation is called a biharmonic equation. The most general solution of this biharmonic equation was given by Mitchell in the 1800s itself. So what Hertz Givens essentially did was to take this biharmonic solution and then say, I can always set, if it's a partial differential equation with constant coefficients, so you can always look for a solution of the form. I'll write it in the cylindrical polar coordinates, and remember what are the coordinates that we have? It's a r and phi. Okay, r is my radial coordinate at any point. So if I have any point P, then this is given by corresponding radial location from the contact line, and this point at the center, which I'm showing it here now in red, this is my origin. The idea is that any point in the entire flow domain, whether it's in liquid 1 or liquid 2, can be obtained by just knowing the position R and phi. So typically liquid 1 is typically just liquid, that is actually instead of calling it liquid 1 and liquid 2, I should probably call it as fluid 1 and fluid 2. And fluid 2 is typically a gas. So the most common of gas is of course air itself, and primarily the viscosity of the gas, if you recognize that the viscosity of gas is very very small compared to viscosity of liquid, typically it's about 50 times less than viscosity of most liquids. Like you would say viscosity of water is 50 times more than air. You can actually ignore the effect of gas, but we'll come to that later. So what Herns-Cohen essentially, what we can show is that the general solution of this equation can be assumed to be of the form some a, some constant r power lambda plus 1 times f of phi. This is a variable separable solution where in general a and lambda are in general complex constants. Now what do they depend on? They depend on a variety of parameters. These parameters would depend on primarily a. The constant a would depend on, you have to do an expansion here like this. They would depend on the viscosity ratio, the value of the contact angle, and those are the two primary parameters. Velocity itself will not matter because this is a linear problem, so changing the velocity will not change the problem, the solution itself. So you can actually rescale this problem to set a velocity equal to 1. But let's now look at a special case, okay, so that we understand the singularity. Special case of Herns-Cohen solutions. We'll do it for a free surface flow. The idea is as follows. We have a plate like this and a flat interface. And the idea is that at the flat interface, my phi is 0, here phi is equal to alpha, and my interest is only in this region, that's the liquid. My interest is only in the liquid region. Same idea, we will look for a solution in terms of a variable r and phi. And the argument is as follows. We saw earlier that del square of psi is minus omega and del square of omega is 0. The second one, so you have two equations. Rather than writing one single biharmonic equation, let's write down these two equations. Now, the second equation is coming from the momentum equation, the Stokes equation. And the first equation is coming from the definition of the vorticity. So remember that the continuity equation doesn't have to be explicitly written because it's implicit. It's the moment we define a stream function, continuity equation is automatically satisfied. In fact, continuity equation allows us to define a scalar called a stream function. So we will now do it in the r theta coordinates. Okay. So r phi coordinates. The argument is as follows. U r, I will take it to be 1 by r del psi by del phi. I hope I've been writing this correctly. Del phi by del phi. And u theta will be minus del psi by del r. Therefore, omega, which is a scalar in this case, will simply be 1 by r del by del r of r u theta minus 1 by r del by del theta of ur. I'm just writing down what is the definition of r in cylindrical polar coordinates. And if you now substitute ur and u theta as defined here, then you basically get del square of psi is minus omega as you get. But more importantly, what you get is you get 1 by r del r of r del psi by del r plus 1 by r del by del phi of del psi by del phi minus omega, right? And this is the expression for this. And similarly, this is del square psi is minus omega. This is one equation. We also have del square of omega is also 0, and this essentially becomes 1 by r del by del r of r del omega by del r plus 1 by r del by del phi of del omega by del phi is 0. This is my second equation, right? Now, what we want to essentially speculate is that we can speculate that both stream function and vorticity should be finite as r goes to 0. The reason is because if these equations have to make sense, that we don't want these quantities to diverge as r goes to 0. So we can say we expect both omega and psi to remain finite as r goes to 0. At the very least, we can let them go to 0, but they themselves cannot go to infinity, right? So we can assume a local form for omega and psi using Taylor series expansion near r equal to 0. The argument is that I can always define psi to be r times f1 of phi plus some order r square, and similarly I can also define omega to be r times f2 of phi plus order r square. Note that we are looking for a single phase flow, so viscosity is 0 here. It is passive gas. It's a free surface problem. Well, I've already written that here. It's a free surface problem, right? And so we don't have to worry about what's happening on the other phase. Now we can substitute psi and omega into, let's label these equations. Let's call this equation as star and this equation as double star. So let's substituting psi and omega into equation star and double star. I won't do the analysis here because it's straightforward substitution and differentiation. We don't have to worry about this order r square terms. We only consider psi to be r times f1 and omega to be r times f2. So remember, f1 and f2 are functions of phi alone, and therefore any derivative with respect to phi will be a total derivative. Even though in star and double star equations, you see that the derivatives of phi are partial derivatives. If we substitute psi and omega into these, what do we get? We get f1 double prime plus f1 will be minus f2. That's the first equation. And f2 double prime plus f2 will be 0. That's the next equation, where anything to the prime in this case is nothing but d by d phi. So f1 double prime is d square f1 by d f1 square. So we've got basically two equations, right? Coupled equations. So the idea is that if you look at the second equation is f1 f2 double prime plus f2 is equal to 0, and this gives me solutions which are f2 of phi, which will involve a sine phi and b cos phi, or let's call it as a prime, maybe I'll just call it as a1 sine phi plus b1 cos phi, right? Those are the fundamental solutions of this equation. Now what we will do is we'll take these fundamental solutions and substitute them into the above equation for f1, but the f1 fundamental solutions are f1 are also sine phi and cosine phi. So what we now have is inhomogeneous equation for f1, and the general solution for f1 simply becomes for this inhomogeneous equation, we simply get f1 of phi will be a sine phi plus b cos phi plus c phi sine phi plus d phi cos of phi. That's what we have. So this is an important step, because once we've got this, we have got the general solution. So now once we get f1, all that we need to do is substitute this into these equations, which is we can get psi and omega. So once you get f1, you can calculate f2, and once we get f2 as well, then you can basically get the stream function, and you can also get the vorticity. Okay, but let's basically look at this equation that we have here. A, B, C, D are obtained with using boundary conditions at phi equal to 0, that is, let me put that here, at phi equal to 0, that's the interface, and phi equals alpha, that's the solid. So the solid would be that no slip condition has to be met, and no slip condition, if you remember the geometry, or let me just make the geometry again. So we have an interface here. So at any point here you have two conditions. You have two velocities. This will be radial velocity and this is the azimuthal velocity. And over here you have the radial velocity and you have the azimuthal velocity. So basically no slip condition would mean u r is 0 on the wall, and u r is 0 on the wall simply means del psi by del theta is 0 on the wall, right? And let me write that down. Del psi by del phi, not theta, del phi by del phi. All of this is supposed to be phi, sorry. I hope I've mentioned this as phi. This also has to be corrected. Please correct this. This would be just del phi. I usually tend to write phi, but then since I started with, well, anyway, it doesn't matter. So we have del psi by del phi on the solid. This will be equal to 0. We also have the condition of velocity being finite on the wall. That is, ur will be non-zero at the wall, and ur will simply be del psi by del phi. 1 by r del psi by del phi will simply be u, let's call it as uc, where this is the motion of the plate. Similarly, at the interface, you have stress-free condition. Therefore, you have again, and you have azimuthal velocity 0. Azimuthal velocity 0 simply means del psi by del r will be 0 at the interface, right? And you also will have another condition, which is stress condition, that is tau r theta is also 0 at the interface, which you have to write it in terms of the velocity, right? So this will involve derivatives of the velocity, therefore second derivatives of the stream function. But I will not go into details, but if you do, you can actually write down the conditions, and these are fairly straightforward standard conditions that we have done several times in the course. What you now get is the constants. The constants become A will become UC of sine of alpha by alpha minus 1 by cosine of alpha whole inverse. B will be 0, C will be 0, and D essentially becomes UC by, again similar to this, but it's slightly different. So, well, the exact values, as far as this particular lecture is concerned, the accuracy of this is something that I'd expect you to check, but I want to focus on the physics of the problem. Now, once you get this, you can calculate the shear stress. And shear stress in this case will be tau r phi, and this essentially becomes minus 2 times capillary number by r times d sine alpha, where capillary number is our well known mu u c by gamma, right? Therefore, what does it tell you is the shear stress diverges as r goes to 0. Okay. This is also true for the dissipation. The dissipation also diverges. So does the pressure. So does the tangential force on the wall. So all of these quantities diverge, and these divergences are of different kinds. Some of them are algebraic divergences like this, like a 1 by r kind of divergence. In some cases, we have a logarithmic divergence, which is a far more serious divergence. So this is basically the same paradox, same singularity that we found. This is essentially the Her and Scriven singularity. Okay. So, well, we know that nature doesn't have the singularity. So, which means that the one obvious conclusion that we can come to is, well, it's not obvious actually in a way. One conclusion that we can come to is that the classical equations that we have used, which is Navier-Stokes equations with the classical boundary conditions of no slip and so on, are not valid. Okay, so there have been a lot of attempts to introduce new physics near the contact line and also model this in some way. So I'll briefly talk about some of the modeling strategies that people have employed over the years, and what is the goal of these modeling strategies also I will briefly touch upon. So we'll look at two things in the next lecture: ways to alleviate the singularity, and what kind of what do these contact angle models primarily achieve. Okay, so I'll see you around in the next lecture. Thank you.